For today's lesson, we are going to be using Desmos.com to help us kind of explore and discover some things about the transformations of trig functions and their graphs. So as you can see on my screen here, I have our notes pulled up and I also have Desmos.com ready to go. So I'm going to walk you through the first part of these notes and then I'm going to have you finish them on your own. So our first directions say go to Desmos.com and graph the equation y equals the sine of x. So I'm going to graph y equals the sine of x. So as you can see, our periodic function, our sine function, shows up just like we normally like it. However, my axes aren't really in like labeled by pi, like in steps of pi like we normally like. So to fix that, we're going to follow the next directions. Click on the wrench icon in the upper right hand corner and adjust the x and y axis. So if you click on this wrench icon and here where it says x axis and y axis, we can change the domain and the range of what's shown on our coordinate plane. And we can also change the step. So for the x-axis, we're going to change the domain to -2 pi. And to type pi, you can literally just write pi. And Desmos automatically changes pi to pi, the symbol for us. Then on the other side, we're going to change the maximum to 2 pi as well. And then we are going to do pi for our steps, so that way on our x-axis it'll count by pi for us, just to make our lives a little easier. And then for the y-axis, we clearly don't need our range to go from like -11 to +11, so we're just going to change it to -4 to +4, just to like tighten up our window. And then here you can change your step to 1 if you want. You can change it to 1/2. I didn't give you specific directions on the notes because I don't really care what your step is for the y-axis. I'll just leave it at 1 for now. All right, so now we kind of have a clear picture of y equals the sine of x and what our y values are at each pi interval, which is how we normally talk about y equals the sine of x. So now we're going to follow the directions here and we're going to answer each question. So for number 1, for equation 2, so equation 1 is y equals the sine of x. We are going to type y equals a times the sine of x. So for equation 2, we're going to leave our original graph alone and we're just going to add y is equal to a times the sine of x. Now when it pulls up add slider for a, you're going to select that. You're going to go ahead and add that slider. So now play with that slider. So if you move to the right, as you can see, a changes its values to positive numbers. So like here's +2, here's +3, here's +4, etc., etc. Then if you slide it to the left of 0, you are doing negative values for a. So we need to answer 2 questions. The first is, when a is positive, how does the graph compare to the parent function? When a is negative, how does the graph compare to the parent function? So if we're at 1, we match the parent function. If a goes off in that positive direction, what happens is as a gets like higher or increases in value, our amplitude increases. So if a is 3, the amplitude went from 1 to 3. If a is 4, the amplitude is going to go from 1 to 4, etc. So then let's go ahead and describe that. So the value of a changes the amplitude. And when a is positive, the sine function like maintains its like general shape, right? I guess we don't need to type that though. So the value of a changes the amplitude. Well, what happens when a is negative? So when a is negative, not only does the amplitude change, but it also takes our curve and reflects it over the x-axis. So if you make a -1, The amplitude is still 1 on this blue line here, but it took our maximum and suddenly made it a minimum. So the value of A still impacts the amplitude. However, the negative A values also reflect the sine function over the x-axis. So now we're going to do the same thing with number 2. So for number 2, we're going to change our equation 2 here. And instead of having y equals a times the sine of x, we're going to change it to y is equal to the sine of bx. So you don't need the a slider anymore. So y is equal to the sine of bx. Now you're going to add a slider for b. So again, what does the value of b do to our graph? What does the positive b value do? What does the negative b value do? So for positive b, interesting. And then for negative b, let's look at positive 2. So it looks like what it's doing is a horizontal compression. So if we go from A, here's B equals 1, and then for B, if you go slowly to 2, you see that instead of having a period of 2 pi, we now have a period of 1. So it reduces the period, and it gives us a horizontal shrink or a horizontal compression. So if B is positive, we have a horizontal compression, and the period becomes smaller the higher the B value. So if you change B to 3, you're compressing it even further. And at 3.5 here, see we have our whole period, one cycle fits like literally right here in the smaller area. Okay. And then what about when B is negative? So let's look at B equals -1. So all B equals -1 did, the period is still 0 to 2 pi, but we've reflected over the x-axis. Then if you do -2, we still have that horizontal compression, but we've also still flipped over the x-axis or reflected over the x-axis. So the value of B still impacts the period, creating a horizontal shrink or horizontal compression. However, the sine function is reflected over the x-axis. Let me change the formatting of this so they match. There we go. So why don't you go ahead and finish this first page without me. Go ahead and do 3 and 4. And play around with x minus c inside the function and then plus d outside of the sine function. And just see what happens. Go ahead and write your observations and then we can talk about it together once you come back. So for number 3, we need y is equal to b, the sine of x minus c. Sorry, I can read. Y is equal to the sine of x minus c. We're going to add a slider for c, and it looks like when c is positive, our graph, I'm going to go back to 0, if I can find 0. Here's 0. When c is positive, that whole function just shifts to the right. When c is negative, the function shifts to the left. So when c is positive, the sine function shifts to the right. And when c is negative, the sine function shifts to the left. I'm going to change the formatting again. There we go. All right, and this stuff should look familiar. When we subtract a value directly from x, it shifted our parent functions to the right. When we added a number to x, it shifted our functions to the left. So we've seen this before when we've graphed and shifted and transformed other parent functions as well. These rules stay the same for our sine functions. And now we need to, get rid of this. So now we're taking the sine of x, and then to the entire function, we're adding this value d. So if d is 0, there's no transformation. It's the same graph as the parent function. But if it's positive, it just shifts that parent function up. And then what if it's negative? We shift down. So the value of d shifts the sine function up. And the value of d shifts the sine function down when d is negative. Moving on to number 5. So for number 5, instead of having the sine function now, we want to explore the same for a cosine function. So you're going to go back here, and instead of graphing a sine function, you're just going to change it to the cosine function. And you're going to have the cosine of x, a times the cosine of x. Add a slider for a, and go through the same steps. Now, that's if you need to. So based on what we did up here, we kind of already know what multiplying a times the sine of x does. We know what multiplying b by x does inside the sine. We know what subtracting c does. What do you think is going to happen when we do the same thing to our cosine function? So you can use Desmos to help you, or you can just use kind of what we already know and understand about transformations to make some educated guesses and then check your answers on Desmos. So why don't you go ahead and press pause on the video, come up with your theories of what transformations will occur, check your work on Desmos, and then press play when you're ready to check your work with mine. So I noticed that when I multiply a times the cosine of x, my amplitude changes based on the value of a, and then if a is negative, my amplitude changes, and I also have a reflection over the x-axis. So I'm going to say the value of a changes the amplitude of the cosine function, and if a is negative, the cosine function reflects over the x-axis. For the cosine of bx, I notice that b impacts my horizontal distance, or my period. So if b is positive and greater than 1, we have this horizontal shrink or horizontal compression. But if b is less than 1 but greater than 0, we have a horizontal stretch. Interesting. And then if b is negative and between 0 and -1, we still have a horizontal stretch, but we also have a reflection. And then if b is less than -1, so a negative number that's over -1, or less than -1, sorry, we still have that horizontal compression and the reflection. So if B is greater than 1, there is a horizontal compression and the period is smaller. If B is greater than 0, oh, hang on, I should say if B is between 0 and 1, there is a horizontal stretch. Then if B is less than -1, there is a horizontal compression and a reflection over the x-axis. Then if B is between 0 and -1, so if B is, let's see, -1 would have to be less than B, which is less than 0. There is a horizontal stretch and a reflection over the x-axis. Then you should have noticed that if you subtract a number directly to x within the cosine, we shift left and right. So the value of C shifts the cosine function left and right. And then the value of D, so the cosine of x plus D, add a slider for D just to check. The value of D shifts our cosine function up and down. So today's assignment, instead of having you print out a worksheet or do some problems on a given worksheet, you're actually going to follow a Desmos activity, which you'll find in a PDF format on our Schoology page. And just follow exactly what it says. Within that week 9 folder, you'll find that PDF and just follow those directions and you should be fine. Shoot me an email if you have a question or you get confused. But that's all the new information for this week. And actually, now that I'm thinking about it, we should go back up here to where we had our values of B and just specifies for the sine function as well. Let's see if it mattered. So for the sine of x and for the sine of x, let's get rid of that and do bx. Add a slider for B. Sorry, you have to excuse my puppy for barking right now. I'm just gonna let him be. So in our sine function, of x here for B's value, if B was greater than 1, we did have that horizontal shrink, right? But what if B is less than 1 but greater than 0? Let's see what happens. We have a horizontal stretch, just like with that cosine function. Okay, and then the same, I'm guessing, for the negative between 0 and -1. Yep, and then over -1. Yeah. So we need to specify that. I am so sorry. So there's a horizontal compression and the period becomes smaller the higher the B value. So if B is greater than 1, that's true. But what about if B is less than 1 but greater than 0? So 0 is less than B is less than 1. Then there is a horizontal stretch and the period is much bigger or greater the smaller the value of b. Let me make sure that's right. So between 0 and 1, where are we? Here's 0. Between 0 and 1, yeah, that period starts to shrink. So the smaller that b value is, so like 0.7 has a greater period than 0.9, for example. All right. Then the same thing is true here. So the value of b still impacts the period, creating a horizontal compression. However, the sine function is reflected. So that was true if b was over -1, right? Or over -1, less than -1. So if b is less than -1, that's going to be the case. But then if b is between 0 and -1, so if -1 is less than b is less than 0, then there is a horizontal stretch and the sine function is reflected over the x-axis. So if b is between -1 and 0, let's get b between -1 and 0. We have that stretch, but it's still reflected. All right, so I'm glad we were able to fix that. I need y'all in my classroom with me when I do these lessons, so that way we can make sure we catch all my mistakes, huh? All right, well, I hope you guys have a good weekend, and I will talk to you next week.